In this chapter, we will be studying systems of linear equations. In this lesson, we're going to look at the number of possible solutions to a system of linear equations.
Okay, now we're going to take a look at solving systems, but we're going to look at it from a little bit more of a theoretical perspective here. Up to this point here, the systems that we've solved in this chapter have always had a solution. There has been a point of intersection between the two lines. Thing is, that's not always the case. Okay, it is possible that the system may or may not intersect. Okay, and so we need to look for that. When they don't intersect, there's no solution. And in fact, it is possible for that to have multiple solutions. And in this particular case here, in this context, that's actually a little bit of a problem as well. And you'll see why I say that in just a second here. So let's take a quick look at the types of systems that you get. There's a little bit of vocabulary you need to get from this. So to start off with, we have intersecting lines. Okay, this is what we've been looking at. Now, notice that between these two lines here, really, in order for these two lines to intersect here, they simply have to have different slopes. Their y-intercepts can be anything. They could be the same. In fact, if they were the same, that would be the point of intersection. Doesn't really matter as long as they have different slopes. That's going to guarantee that they will intersect. And they'll have one solution. And now we call it, when it's got one solution, we call it a consistent system. Now this is really what you got to know. However, we might also state in that context that these two lines are independent of each other. And what we mean by that is when we say independent, it's not possible to take this equation, let's say, and multiply it by something to get this equation. They are very, very different. So there's a consistent system, one solution. But we could draw these two lines like this, and notice when we've got parallel lines, there's no solution. Okay? And in our context here, and from what we've seen in the rest of this course here, we know that this means that the slopes are the same. And they will have different y-intercepts. So same slopes, different y-intercepts. Really important that both of these are now true, and we get no solution. And this is what we would call an inconsistent system. These are also independent. Okay, because it is not possible, again, to multiply this equation by something to get this equation right here. They are very different. Inconsistent, meaning that there's no solution. Consistent means there's a solution. Inconsistent means there's no solution. Okay. Now, in terms of independent right now, at this point here, that might really not make much sense, but give me one more little example here. Now we've got what we call coincident lines. And that's basically two lines that are right over top. It's basically the same line twice. Okay, these things have the same slope and the same y-intercept. Now, you might look at that and say, well, that there's only one equation. Yeah, I know. But let's say, for example, that the one line here had the equation, let's say, negative 3x plus 5. Well, it's possible for me to multiply this equation through by another number, let's say 2, and we get 2y equals negative 6x plus 10. Now, that is technically the exact same line. But I changed the equation a little bit by multiplying it by a constant here. This is what we mean by dependent. Okay? The second equation depends on the first one, which is why we're getting this many solutions. In fact, there's an infinite number of solutions here. Okay? Because every point is a solution to the system. Every point on that on this line satisfies both equations here. Okay? So it is consistent, but they're dependent, and so you're going to get this infinite number of solutions here. That really isn't giving you anything, right? The information really comes out of the scenario here where you've got one solution, one point of intersection. Okay, so now we're going to take a look at some examples. Okay, so this first question, and we're going to do it all together at once here, is telling us to predict the number of solutions for each of the following. Okay, well, based on what I just said, it makes sense to convert these all into slope-intercept form and to look at their slopes and their y-intercepts here. And hopefully by the time we get a few questions in, you're going to start to see some shortcuts here. So in this first equation, here's 1, here's 2. Equation 1, I would bring the x over, so it would become 2y, I'll write it over here maybe, 2y equals negative x plus 6, and then I'll divide by 2, And so y is going to equal negative 1/2 x plus 3. For the second one here, equation 2, all I've really got to do is just bring the x over, so it becomes y equals negative x minus 2. Okay, now notice they've got two very different slopes. In fact, that's the first place I want to look. Negative 1/2, negative 1, different slopes. Therefore, we're going to get one solution. This is a consistent system with one solution. Now notice what's happened here. There was a 1 in front of both of these, but there was a 2 here and a 1 here. Okay? Now I'm just drawing your attention to the coefficients here. Hopefully you'll see in just a couple seconds here, after doing a couple of these, you'll start to see a pattern between the coefficients and the result that we get. Okay? Let's take a look at B. Again, first thing that I'm going to want to do here is convert these into slope-intercept form. So I'm going to isolate the y. So initially I'll get negative 5y is equal to negative 2x plus 30. For that first one, equation 2 will be negative 10y is going to equal negative 4x plus 15. And now equation 1, I'll divide everything through here by 5, and so negative 5. Y equals 2/5 x minus 6. And equation 2, I'm going to divide both sides here by negative 10. And when I divide negative 4 by negative 10, I'm going to get 2/5 x. And when you divide 15 by negative 10, there's a common 5 to both of those. So I'm going to get negative, 3/2. Notice the slopes are the same, but the y-intercepts are different. Parallel lines, okay, so no solution. Now watch what happened here. Watch what happened when you compare these two equations. When I compare the x's and I compare the y's here, how did I go from this coefficient to this coefficient? Well, you multiply by 2. How did you go from this coefficient to this one? Well, you multiplied by 2. Well, it's the same step to go from here to here. However, when I went from 30 to 15, I divided by 2. That was different. So now think about what happens here. When I was solving these, putting these things into slope-intercept form, I used these two numbers to get me the slope, this number and this number to get me the y-intercept. Interesting. Anyway, next one. The second one here, the second equation is already in slope-intercept form. So in that first equation, I'm going to bring the 4x over, so 6y equals 4x plus 6. I'll divide by 6 there, so y is going to equal 2/3 x plus 1. And equation 2 was y equals 2/3 x plus 1. Now notice the y-intercepts, the slopes are the same, the y-intercepts are the same. We have got infinite solutions. Okay, this is a consistent but dependent system. Okay, now in this case you're really not seeing what would happen here. Essentially what would in this case, if I was to multiply that through, if I was to multiply the 3 through, you would get 3y, and then bring this term over, would be 3y minus 2x is equal to 3. And notice in this case here, to go from 6 to 3, divide by 2, negative 4 to negative 2, divide by 2, 6, 3, divide by 2. It's the same step for all three of those different positions. So when it's infinite solutions, it's really just the same thing that you're doing with every single term. If there's no solutions, you're doing the same thing for the x and the y, but it's a different relationship between these two values right here. And if there's one solution, it's not even consistent between the x and the y. Okay, let's take a quick look at some more. We'll finish this off here. Here's equation 1, equation 2. Now just take a quick look at this. Let's see if we can use a bit of a shortcut here. To go from first equation to second equation, look at the coefficients here. I multiply 3 by 2 to get 6. I multiply 5 by 2 to get 10. It's the same thing. So I know that when I simplify this out here, the slopes will be the same. But now notice this. 9 to 18, again, multiply by 2. This is essentially the same line. Okay, so because to go from one equation to the other, I just multiply by 2, there are infinite solutions here. I shouldn't have to solve for y in this case right here. Take a look at this one. Okay, notice that the coefficient of x is the same. It's a half. The coefficient of the y is the same. It's a third. Now, that means that the slopes are going to be the same. But look at the constants on the other side here. Those are different. That implies to me that the y-intercepts would be the same, because remember, I need this number to get the y-intercept if I was to solve for y. So between these two here, I've got the same slopes, but different y-intercepts. There's no solution. These are parallel lines. And in this last one here, you might want to rewrite this just so that they're both in standard form. And so that would make this x plus 4y equals 8. To go from x to 2x, I multiplied by 2. But to go from 4y to y, I divided by 4. Well, there's an inconsistent relationship there, even at that point, between the x's and the y's. So I know that there's different slopes for both of these two lines here. So there's going to be one solution, and that's it. Okay, what is the solution to the system of equations right here? Now, I am going to go through the process of solving this system, because I suspect that based on what's happening in this lesson here, it's going to be one of these two right here. And I want you to see what happens algebraically when you get a situation like this, okay? So, first of all, what I'm going to do is I'm going to put the second equation here into standard form. So, equation 1, 3x minus y equals 8. Equation 2, I'm going to bring this 6 over, so negative 6x plus 2y is equal to negative 16. Okay, now just to compare these things, I multiply 3 by negative 2, multiply negative 1 by negative 2, multiply 8 by negative 2. Okay, these are the exact same line. This is going to have infinitely many solutions. I already know that. But I'm going to solve this system. I'm going to show you what happens here. And I want you to be able to interpret it and not get thrown off by the results, because it is a little weird here. So for example, what I'm going to do here is I'm going to take equation 1 and multiply by 2, and then I'm going to add equation 2 to it. My assumption here is I'm going to do that to get rid of the y, let's say, because they have two different signs here, so I'm going to add them together. But when I go 2 times 3, I get 6, plus negative 6 is 0. 2 times negative 1 is negative 2, plus 2 is 0. 2 times 8 is 16, plus negative 16 is 0. And so in my attempt to solve this system, I get 0 equals 0. Now, that is true. 0 is equal to 0. So what that means is, regardless of the values of x and y, when you try to solve the system, you get a true statement as a result. Therefore, this must always be the case. It must have an infinite number of solutions. Now, let's just say for argument's sake that you got that 0 was equal to 2. Well, that's a false statement. It doesn't matter what you plug in for x and y, because they disappeared, it's always going to be a false statement, in which case the answer would be there was no solution. These lines don't intersect. So those are the two possible results you're going to get. Okay? But yeah, if you get a situation like this, if all of a sudden everything disappears and you get this as a result, understand that that means that this is a consistent system, infinite solutions. Okay, so the question here says, use the graph, okay, right here, to determine the number of solutions for each of the following systems here. Okay, so here's my first system. Y equals negative x plus 5, y equals x minus 3. Okay, so y equals negative x, sorry, was it negative x plus 5? Yeah, it was, negative x plus 5. That's this guy. X minus 3. Okay, that's got one solution. Now, I already knew that because the slopes were different. These are both in slope-intercept form. Slopes are different. One solution. Okay, next one. Negative x plus 5. That's that guy again. And then this question here, 2x plus 2y equals negative 8. Okay, well, I'm going to bring that x over. I'm going to get x plus y equals 5. Now, notice, multiply by 2, multiply by 2, same slopes. Multiply by 2, So I'm going to assume that there's no solution here. Okay. Now, where do we got here? 2x. Oh, there's a little bit of an error here because that one's not, that doesn't work here. 2x minus, okay, if you were to solve for that, let's just graph that in here just so that we're clear here. If I was to solve for y here, this would be negative 2x minus 8 divided by 2. Y equals negative x minus 4. That's actually the exact same line as this one. Not this equation right here. That's going to be this one again. And so there is no solution. Whoops, sorry, no solution. Yeah, this one's pointing to the wrong line. It should be pointing to this line. Here, 2x plus 2y equals negative 8. Y equals negative x minus 4. Well, we've just established that those are pointing to the same line there. Oh, I see what happened here. Sorry. This one just got rewritten here. Sorry, it is 2x plus 2y equals negative 8. I didn't even notice that right away. So they are both pointing to that. This one's just a lie, a red herring. Here they are the same, so here there are infinite solutions. They are the exact same lines. Okay, now for this last question here, we got a little bit of work to do, but it's a good question. It's a really good question. For values of k, does this linear system have either exactly one solution or infinitely many solutions? Now, look at the fractions here. That's not comfortable. I'm going to get rid of the fractions here. I'm going to take equation 1, equation 2 here. What I'm going to do to start off with, I notice that the least common multiple of my denominators here is going to be 6. I'm going to multiply equation 1 by 6. 6 times a half is going to be 3. 6 times 5/3 will be 10. And 6 times 2 is 12. So here's my new equation 1. Here, I really only have to multiply this one by 2 to eliminate my denominator, and I will get, here's equation 2. This is going to be 2kx plus 5y is equal to 6. Now, in order to have exactly one solution, okay, watch how this works here. Watch how this works. Or maybe I should look at it like this. Let's answer it like this. To get infinite solutions here, this has to be consistent. 12 divided by 2 is 6. 10 divided by 2 is 5. So 3, in order to have infinitely many solutions, 3 divided by 2 has to equal 2k. Oops, sorry, can't see that. In order for there to be a consistent relationship all the way across here, 3 divided by 2 must be equal to 2k. And if I divide both sides here by 2 to get k by itself, I get 3/4 is equal to k. So as long as k is equal to 3/4, there's going to be infinitely many solutions here. Now, exactly one solution. Now, as long as the slopes are different, I'm going to get a solution. I will have a solution here. So if I plug 4/3 into this, okay, then you get 3/2 here. And if you multiplied everything by 2, then you would get 3 plus 10. 3/4 as a value for k gives you the same slope for both of those. So the easiest thing for me to do here is to say, well, then, okay, k can't equal 3/4. And as long as that's true, you will get only one solution.